Hello everyone. In this lecture, I'm going to discuss the collision of rigid bodies. That is, I'm considering a rigid body. In this situation, it is a rod of length L and mass capital M. And I'm considering a particle of mass m or a ball of mass small m moving to the right with a velocity v0, and it is hitting or incidenting on this rod, which is not fixed at any point, which is free to rotate as well as translate. Then how can we handle this situation? Because when this is a rigid body, which is not a point object, the line of action of this impulsive force produced by the collision is not passing through the center of mass, because of which this impulsive force may produce rotation also, due to which after collision this rod will undergo both translatory motion and rotatory motion. Translation of center of mass, that is velocity of center of mass, is in this direction, and rotation about the center of mass, that is in this sense it will rotate. Now, in the first question that I would like to ask is, what is the velocity of center of mass and what is the angular velocity of the rod? First thing, I wanted to calculate velocity of the center of mass and angular velocity of rod. Okay, so in calculating all these things, I will show you how to apply conservation of angular momentum, conservation of linear momentum, and law of restitution. For that purpose, I am considering this situation. First thing that I would like to calculate is velocity of center of mass and angular velocity of rod. For calculating this, here I am making an assumption. What is that assumption? After collision, this ball of mass m is coming to rest, and the collision between this rod and the ball is perfectly elastic. That is, coefficient of restitution is 1. By keeping those assumptions in my mind, I would like to write down the expression for velocity of center of mass. For that purpose, first we should consider what is system. The system is the ball and the rod. For this system, I wanted to apply conservation of linear momentum, CLM, conservation of linear momentum. First, I should check whether I can apply conservation of linear momentum or not. For this purpose, we should check, is there any external impulsive force? It is not the force that we should consider when collision is considered. It is the impulsive force. Okay, is there any external impulsive force acting on the system during the collision or not? When this ball collides with this rod, okay, the only force that is acting between this body and this body is the impulsive force produced by the collision only, which is an internal force for this rod and ball system, because of which you can apply conservation of linear momentum. So what is the initial momentum of the system? Rod is at rest, only ball is moving, because of which its initial momentum is m into v0 is equal. What is the final momentum? My assumption is ball is coming to rest, because of which rod is moving to the right with the center of mass of the rod is moving to the right with velocity vc. So capital M into vc. This is equation number 1. Through this, what I can write? Velocity of center of mass vc is equal to small m into v0 divided by capital M. This is what? This is how I calculated velocity of center of mass. To find out angular velocity of the rod, second thing that I am considering here is I am applying conservation of angular momentum. I am applying conservation of angular momentum. Here we should be very careful, because with respect to which axis you are applying conservation of angular momentum. And here one more thing you should keep in mind. Angular momentum may or may not be conserved in every collision. And one more thing, may or may not be conserved about every axis. First, we should consider the axis about which the angular momentum is conserved. But here I would like to tell you a thumb rule. Whenever linear momentum is conserved, angular momentum is conserved about any point of the rod. One more time I am repeating this statement. Whenever linear momentum is conserved, angular momentum is conserved about any point of the rod. This is first and very important thing regarding the application of conservation of angular momentum, because to make you clear, it's somewhat clear. I am deviating from this situation. I am considering another situation in which the rod is fixed at this point. Same situation, but only difference is here the rod is free to rotate, here the rod is hinged at one point. In this situation, if the ball is hitting at one of its ends like this, then what happens? Here, linear momentum is not conserved. Linear momentum is not conserved. Here, linear momentum is conserved. The difference between this and this situation is here linear momentum is conserved, here linear momentum is not conserved. Why? Because when ball comes and hits this rod, okay, here it is hinged. So the very instant an impulsive force is generated, what happens? This hinge in turn will apply an impulse force. Okay, so if the impulse force due to this rod is to the right direction, the resultant impulse force applied by this hinge, okay, will oppose the impulse force acting on this rod. So this impulse force comes into picture. The force acting at the hinge is impulsive in this case, because as another impulsive force is coming into the picture, here the linear momentum is not conserved. So when linear momentum is not conserved, we should be very careful while applying the conservation of angular momentum, because angular momentum is not conserved about each and every point of this rod. Angular momentum is conserved only about angular momentum AM. Angular momentum is conserved only about what is that point? Hinge. Here angular momentum is conserved about hinge only, because linear momentum is not conserved and the hinge force is applying some impulsive force. But whereas in this situation, as it is not fixed at any point of the body, what happens? Linear momentum is conserved. When linear momentum is conserved, you can apply conservation of angular momentum with respect to this end, or with respect to center of mass, or with respect to this end, or any point on this body. You can apply conservation of angular momentum. So this is a major difference and very important point that we should keep in mind while applying the conservation of angular momentum. When linear momentum is conserved, it is not must that angular momentum should be conserved. It depends on the axis of rotation. Okay, so here with respect to hinge only angular momentum is conserved, and with respect to all the remaining parts of this body, the angular momentum is not conserved. Again, I will come back to this situation with a problem. First of all, let me finish this. Okay, as a matter of fact only, I consider this in between. Okay, now let me come back to this problem. So here, as the linear momentum is conserved, angular momentum can be conserved about any point. So the best choice that I would like to consider here is, you can conserve it with respect to one of its endpoint A, or center of mass C, or another endpoint B, or any arbitrary point P, any point. But here, the best choice that I would like to consider is with respect to A. I am applying conservation of angular momentum with respect to point A. What is the advantage in considering point A? Because with respect to point A, okay, the orbital angular momentum of particle M before collision and after collision is 0, because the line of action of this velocity or the impulsive force passes through A. Because of each, what happens? Orbital angular momentum, or simply angular momentum of this M with respect to A is 0. Therefore, angular momentum of the system before collision is 0, because rod is already at rest. The line of action of this impulse is passing through A, because of which angular momentum or velocity, line of action of velocity is passing through A, because of which angular momentum of small m is 0. So total angular momentum of the system before collision about A is 0. Next, what happens after collision? What's happening? This body is coming to rest. Of course, if it moves back also with respect to A, it is zero only. That is the advantage in writing conservation of angular momentum with respect to A. That is the point of collision, with respect to the point of collision. Okay, now then what is happening? The rod is translating as well as it is rotating, because of which rod will be having both orbital angular momentum and spin angular momentum. So because of which I center of mass into omega. In which sense it is rotating? It is rotating in this sense, that is in counterclockwise sense, because of which it is pointed along the k cap direction, plus m into r center of mass cross v center of mass. This is orbital angular momentum. That is equal to what I can write, I center of mass. Moment of inertia of rod with respect to one of its end is m L square divided by 12 into omega, which is along k cap, plus m into r center of mass. So position of center of mass with respect to A is how much? Distance from here to here is how much? L by 2. And if you take this as x-axis, this is y-axis, because of which I have taken normal to the plane towards me as z-axis. So in the direction of r bar, this is j cap cross, okay, velocity of center of mass. Center of mass is moving to the right direction, vc, which is along I cap. That is equal to, what are you going to get here? M L square divided by 12 into omega, which is along k cap, plus m L by 2 into vc, m L vc divided by 2. So j cross I is minus k cap. So through this, what you can write, that implies all through this m L divided by 2 gets cancelled, and you can send it to the right direction. So what you will be getting, L divided by 6 into omega is equal to vc. Okay, so this is the relationship between velocity of center of mass and angular velocity. So to find out what is omega, what you can do, you can substitute this in this expression. In terms of V naught, you will be getting. So L divided by 6 into omega is equal to, what is Vc? Vc is m into V naught divided by capital. So this is what I can say about angular momentum up to now. Next, by applying law of restitution, I will find out the relationship between small m and capital M. Here, you can find the relationship between capital M and small m by applying conservation of energy also. But to show you how to apply law of restitution, okay, I am considering the first method only. What is my first method? By applying law of restitution. Okay, so what is the law of restitution here? E is equal to coefficient of restitution. E is equal to V21 divided by U12. In which direction you should write? This is very careful. You should be very careful while writing down this. These components you should take along line of impact. Okay, line of impact. That means along this line only you should write down this V21 and U12. Okay, so in the assumption itself, I assumed that coefficient of restitution as 1. That is, I said it is a perfectly elastic collision. Okay, and what is the initial velocity of the ball? That is U1 is equal to how much it is? V0 only. And U2 is how much? 0. And V1 is equal to how much? After collision, ball is coming to rest, because of which V1 is 0. And V2, what is the velocity of 2? That is nothing but velocity of A. Okay, because it is a combined translation and rotatory motion, no? Therefore, velocity of A is equal to what I can write? Velocity of A with respect to center of mass plus velocity of center of mass. Okay, that is equal to velocity of A with respect to center of mass. A with respect to center of mass, A will be in pure rotatory motion. That is how much it is? Omega into distance from here to here is how much? L by 2. Okay, so when it is rotating, this is in k cap direction. This is, omega is in k cap there, and its tangential velocity will be in right direction, because of which omega into L by 2 will be in which direction? I cap only. Plus velocity of center of mass. Center of mass also is moving to the right direction, because of which I can write down V. Okay, so at this instant, this particle velocity of A with respect to center of mass is in this sense, and at the same time, velocity of center of mass is to the right direction. Okay, which is along I cap only. So these things I wanted to substitute out here. Therefore, V21 is equal to V2 minus V1 divided by U1 bar minus U2 bar along line of impact. That is equal to, that implies U1 minus U2 should be equal to V2 minus V1. U1 minus U2. U2 is anyhow 0, because of which V1, which is along I direction, is equal to V2 minus V1. V1 is anyhow 0. So V2 only. So V2 bar is how much we got? Omega into L divided by 2 into I cap plus velocity of center of mass. Okay, V1 is nothing but V0 only, because here we assumed it as V0. This is V0, VC only. Okay, so here we have two relations in concerning omega and V0, because I can substitute here what is VC. Am I right? So that is equal to, all are I caps only, so I am dropping I caps now. Therefore, V0 is equal to omega into L divided by 2 plus VC. VC is equal to how much we got? M into V0 divided by capital M. Okay, here I want to find the relationship between small m and capital M. So you can eliminate omega, or if you want omega, you can eliminate V0. Anything you can do. What I will do is I will eliminate omega. From this expression, omega is equal to what I can write? Omega is equal to M into V0 divided by capital M. M into V0 divided by capital M into this. If you send it to 6 by L, you will be getting 6 by L into already one L is here. So you write it. So here, what's happening here? Okay, so L gets cancelled. Okay, 6 plus 1, 7 M into V0 divided by capital M is equal to V0. Oh, sorry, here 2 I forgot here. This 2 ones are 2 3s are 3 plus 1 4. Okay, this is 4. 4M V0 divided by capital M is equal to V0. So V0 gets cancelled. That implies ratio of masses small m divided by capital M is equal to how much you will be getting? 1 divided by 4. Okay, this is the relationship between the masses such that after collision body comes to rest. Okay, now if we substitute back into this expression, okay, we will be getting omega as omega is equal to what you will be getting? Small m by capital M is how much? 1 by 4 into V0 into this will become 6 divided by L. 6 divided by L. So that is equal to how much we will be getting here? 2 2s are 2 3s are. So 3 V0 divided by 2. Okay, so by applying conservation of linear momentum, I calculated velocity of center of mass. By applying conservation of angular momentum, I draw the relationship between angular velocity and V0. By applying law of restitution, I found the relationship between the masses such that the body comes to rest. And by using these two equations, I wrote down the expression for angular velocity in terms of initial velocity of the particle. Okay, next one more important feature is when body is undergoing translatory and rotatory motion. Okay, then what happens? there will be a point, either it could lie on the rod or outside the rod, okay, which is momentarily at rest. That is called instantaneous center of rotation, ICR. Now, as this is point number 2 and this is point number 3, as a fourth point, I want to locate the instantaneous center of rotation. So when the body is moving like this particle velocity is in this direction, velocity of center of mass also to the right, and it is rotating in this sense. Okay, I'm considering this rod again over here. Okay, I wanted to consider a point P on the rod which is momentarily at rest, which is called instantaneous center of rotation. So here you should be very careful, because this instantaneous center of rotation may lie up above the center of mass or below the center of mass. I don't know where it can exist, but here one hint I can give you, because when this particle is imparting at this point, okay, it will impart its velocity depending on their relative masses to this point, because of which this point will have a velocity in this direction, and center of mass also has a velocity in this direction. As you keep on moving from this end to this end, what happens? The velocity, the magnitude of velocity of the particles keeps on decreasing. So like this, it keeps on decreasing. At some point over here, what happens? It could be over here, or sometimes it may lie outside the rod also. I'm assuming somewhere over here. Okay, what happens is, for this point, the velocity becomes 0. If you call this point as Vp becomes 0. Now I am writing down the condition for velocity of P. Therefore, Vp is equal to 0. What is the expression for Vp? Vp with respect to center of mass plus velocity of center of mass. That is equal to velocity of P. I'm assuming that this P is at a distance, because I don't know whether it is inside the body or outside the body, because of which I'm calling this distance as y from the center of mass. From center of mass, this point, I'm assuming that it is at a distance y. So velocity of P with respect to center of mass is how much? It will be in rotation. With respect to center of mass, body will be in a state of rotation, because of which omega into, okay, at this instant, okay, when the rod is rotating like this, its tangential velocity will be in left direction, omega into y, which is along minus I cap direction, plus velocity of center of mass is to the right direction, which is Vc along I cap. So everything altogether, it should be 0. Through this, what you can write? Omega y is equal to, what I can write? V into C. Okay, so therefore the location of point P, that is y, which is instantaneously at rest, is given by Vc. What is Vc here? Just now I calculated m v naught divided by capital M. M into v naught divided by capital M into 1 divided by omega. What is omega? 3 v naught divided by 2m. Okay, 3 v naught divided by 2m. That is equal to, just now I calculated here relationship between small m and capital M. Okay, small m by capital M is how much? 1 divided by 4 into v naught into, okay, this you can write it as 2l divided by 3 v naught. So here what happens? V naught gets cancelled. 2 1s are 2 2s are. So therefore location of the point which is instantaneously or momentarily at rest is given by 2 3s are 6, l divided by 6. So when a body, rigid body, is undergoing translation plus rotatory motion, there is a point which is at rest instantaneously. The body is at rest with respect to that point only for a moment of time. So that location is given by L by 6. That is, from the center of mass, the distance of instantaneous center of mass is instantaneous center of rotation is L by 6. So this distance is L by 6. Okay, this is how we calculated whatever it is the thing that is possible by applying conservation of linear momentum, angular momentum, and law of restitution. And one more thing I calculated here is locating the instantaneous center of rotation. Okay, in my next lecture, I will consider this case. That is the case in which the body is hinged at one point.